Hello viewers, today we are going to see about chapter 6.12 collisions. In physics, we study motion, that is change in position. At the same time, we try to discover physical quantities which do not change in a physical process. The laws of momentum and energy conservation are typical examples. In this section, we shall apply these laws to a commonly encountered phenomena, namely collisions. Several games such as billiards, marbles, or carom involve collisions. We shall study the collisions of two masses in an idealized form. Consider two masses m1 and m2. The particle m1 is moving with speed v1I, the subscript I implying initial. We consider m2 to be at rest. No loss of generality is involved in making such a selection. In this situation, the mass m1 collides with the stationary mass m2, and this is depicted in figure 610. So you have a mass m1, m2. This mass m1 collides with m2. Initial velocity of mass m1. So when it collides, this m2 and m1 is colliding m2, and m2 may go this way, m1 may go this way with an angle theta 1 with v1f. Final velocity of mass m1, here final velocity of mass m2. This is x-axis, this is y-axis. The masses m1 and m2 fly off in different directions. We shall see that there are relationships which connect the masses, the velocities and angles. Okay. Now we will see elastic and inelastic collision. In all collisions, the total linear momentum is conserved. The initial momentum of the system is equal to the final momentum of the system. One can argue this as follows. When two objects collide, the mutual impulsive forces acting over the collision time del t cause a change in the respective momenta. That is, del P1 is equal to F12 del T, del P2 is equal to F21 del T, where F12 is the force exerted on the first particle by the second particle. And similarly, F21 is likewise the force exerted on the second particle by the first particle. Now from Newton's third law, F12 is equal to minus F21. This implies del P1 plus del P2 equal to 0. The above conclusion is true even though the forces vary in a complex fashion during the collision time del T. Since the third law is true at every instant, the total impulse on the first object is equal and opposite to that of the second. On the other hand, the total kinetic energy of the system is not necessarily conserved. The impact and deformation during collision may generate heat and sound. Part of the initial kinetic energy is transformed into other forms of energy. A useful way to visualize the deformation during collision is in terms of a compressed spring. If the spring connecting the two masses regains its original shape without loss in energy, then the initial kinetic energy is equal to the final kinetic energy, but the kinetic energy during the collision time del T is not constant. Such a collision is called an elastic collision. On the other hand, the deformation may not be relieved and the two bodies could move together after a collision. A collision in which the two particles move together after the collision is called completely inelastic collision. The third case, the intermediate case where the deformation is partly relieved and some of the initial kinetic energy is lost, is more common and is appropriately known called as inelastic collision. So we have three types of collision: elastic collision, completely inelastic collision, and inelastic collision. Okay, now we will see collisions in one dimension. Consider first a completely inelastic collision in one dimension, then in figure 610. So now we will come back to the main diagram 610. You have two masses. M2 is static, M1 is moving with the velocity, initial velocity, and hitting M2, and M1 may go this direction and M2 may go in this direction with an angle theta 1 and theta 2. Considering this diagram in our mind, let us proceed with the derivation. Theta 1 equal to theta 2 equal to 0. So we are dealing with one dimension. So therefore in this diagram, this angle and this angle, theta 1 equal to theta 2 equal to 0. That means this angle is 0, this angle. That means once that this body hits M1 hits M2, it is moving along the same direction. Okay, so it comes under completely inelastic collision. So theta 1 equal to theta 2 equal to 0. So we know by momentum conservation, M1 V1I is equal to M1 plus M2 is the total mass into Vf. So initially, if you look into the diagram, M1 V1I, but once it is striking with this, it should be equal to M1 plus M2 into Vf, where Vf is the final velocity. This is momentum conservation. From this, Vf is equal to M1 divided by M1 plus, bring this term this side, M1 plus M2 into V1I. Now, the loss in kinetic energy on collision is del K. So we must see half mv square is the total energy before collision, and after collision minus half m1 plus m2 into vf square. That is, when this object hits m2, m1 is hitting m2, and before hitting, the total kinetic energy of this system is half mv square, which is half m1 v1I square. And once this hits m2, so we will be having half m1 plus m2, because m1 has collided with m2, so m1 plus m2 into vf square. So we have to subtract from the initial to the final. So you will get the loss in kinetic energy. Now if you expand this, half m1 v1 square minus half m1 vf square plus half m2 vf square. But from equation 623, we know that vf is equal to m1 divided by m1 plus m2 into v1f. So substitute vf, the value of vf here, that is vf square means m1 divided by m1 plus m2 the whole square and v1I square. That's what we are substituting here. So if you substitute this term m1 plus m2, denominator we have two terms, both one term will get cancelled, and therefore you will be having half m1 v1I square minus half m1 square divided by m1 plus m2 into v1I square. Now half m1 v1I square is a common term. You pull it outside. So this will become 1 minus m1 divided by m1 plus m2. Okay. Now if you simplify, you will get 1 by 2 m1 m2 divided by m1 plus m2 into v1I square, which is positive quantity as expected. Consider next an elastic collision. Using the above nomenclature, with theta 1 equal to theta 2 equal to 0, the momentum and kinetic energy conservation equations are, first we will see the momentum conservation equation. m1 v1I is equal to m1 v1F plus m2 v2F. Then kinetic energy equation is half mv squared throughout, but multiplying by 2, those 2 will get cancelled. Therefore, you will be having m1 v1I squared is equal to m1 v1F squared plus m2 v2F square. Okay. So this is kinetic energy equation. The first equation is momentum equation. Now equation 624 and 625. So using these two equations, you will get the answer as v2F is equal to v1I plus v1F. Okay. So this derivation I will show at the end how you got this. v2F is equal to v1I plus v1F. Now you substitute this in equation 624. This v2F is substituted here, and you will be getting two equations. v1F is equal to m1 minus m2 divided by m1 plus m2 into v1I, and v2F is equal to 2m1 v1I divided by m1 plus m2. Thus the unknowns v1F, v2F are obtained in terms of knowns. m1 mass 1 we know, mass 2 we know, and the initial velocity also we know. That means we know these three terms. Using these three terms we can find out v1F and v2F. Now we will see the special cases of our analysis. If the two masses are equal, m1 is equal to m2. So if this is equal, this will become 0. Therefore v1F equal to 0. Here if m1 is equal to m2, say m2 in the place you put m1, so you will get 2m1, 2m1 gets cancelled, and v2F, final velocity of second object, is equal to initial velocity. The first mass comes to rest and pushes off the second mass with its initial speed on collision. That's the meaning. Initial speed velocity is equal to final velocity. So therefore what happens is the first mass comes to rest and pushed off the second mass with the initial speed on collision. Now we have case 2. If one mass dominates, that is m2, assume m2 is very much greater than m1. So in this equation, m2 is very much greater than m1 means m1 is negligible. Here again m1 is negligible. So what we have is m2 gets cancelled, and v1F is approximately is equal to minus v1I. That is the final velocity of mass m1 is approximately equal to initial velocity of mass m1. In the second case, if m2 is very much greater than m1, so m2 is very high value and this becomes negligible. A negligible value divided by a high value in the denominator makes v2F as 0, approximately 0. That is, final velocity of the heavier mass becomes to 0. That is, the heavier mass is undisturbed while the lighter mass reverses its velocity. That's the meaning, and this is two important equation you have to remember. Now what we have to see is we have to see the proof for getting this relations, this relation and this one. V2F is equal to V1I plus V1F. We will see the proof now. So we have M1 V1I is equal to M1 V1F plus M2 V2F. Momentum equation, and the kinetic energy is M1 V1I square is equal to M1 V1F square plus M2 V2F square. This we already have. So from second equation, what you do is keep this term here and bring this term this side. So you will get this equation. V2F square you bring to the other side, it comes to the denominator. Now what you do is you put this value in this equation, first equation. So you will be getting M1 V1I is equal to M1 V1F. In the place of M2 you substitute this M1 V1I square minus M1 V1F square by V2F square into V2F. Now if you carefully see, you expand this equation. So you will get M1 V1F, you are multiplying this with the first term and the second term, you will get this. Now M1 is constant throughout, so cancel out M1, and then what you do is you multiply this equation by V2F. So M1, you expand this, M1 is a common term, it gets cancelled, and multiplied by V2F throughoutly. So if you multiply by V2F, here V2F cancel, and this term will be multiplied by V2F. Okay, now V1I, V2F, this term, you bring this term to the other side, minus V1F, V2F is equal to V1I plus V1F into, because A square minus B square, A plus B into A minus B. Now common term here is V2F, so remaining terms you put inside the bracket, these two terms gets cancelled, and V2F is equal to V1I plus V1F. This is the proof for equation 626. Next we will see this proof. Now we have from equation 624, M1 V1I is equal to M1 V1F plus M2 V2F. So M1 V1I is equal to M1 V1F as it is M2, and V2F we know V1I plus V1F. Already we got this relation. You substitute in this place, so this becomes M2 V1I into M2 V1F. Now what you do is M1 V1I is in the left hand side, M2 V1I, this term you bring the other side, and between these two V1F is the common term. So V1F is equal to V1I into M1 minus M2. V1I is a common term, bring this V1F will become M1 plus M2 will come to the other side. So V1I into M1 minus M2 divided by M1 plus M2. This is the proof for equation 627. And the proof for the second equation is V1F. We know that V1F is equal to V2F minus V1I. This is from equation 626. Okay. So V1F, M1 V1I, we have the relation M1 V1I is equal to M1 V2F minus V1I. So in the place of V1F, we can substitute this value plus M2 V2F. So this is basically a momentum equation. M1 V1I plus M1 V1I, because you are multiplying this with the second term minus term, this if you move this side it will become plus, is equal to M1 V2F plus M2 V2F. Now V2F is a common term, V2F is equal to M1 into M1 plus M2. The left hand side 2M1 V1I. So therefore V2F is equal to 2M1 V1I divided by M1 plus M2. This is the proof of second equation. So as such, hope you have understood this topic about collisions, especially derivation part of collisions in one dimension, we have assumed theta 1 is equal to 0 and theta 2 equal to 0. That means an object of mass m is eating an object of mass m2, and we have defined all these terms and it is moving along straight line. In that case, we have derived for final velocity of object 1 in terms of its initial velocity, and final velocity of object 2 in terms of initial velocity. So we know the three terms m1, m2 and v1i, therefore we can always find the velocity of v1f and v2f. So that's all about collisions in one dimension. Hope you have understood this derivation. Thanks for watching. Nandri.